Hello, welcome to Earth Analyst. In today's video, I'm going over Planets Better for Life Than Earth documentary. For sleep stars shine distant worlds beyond our reach. Planets may harbor life, unlike our own oceans, swirl unseen. Atmospheres, thick or thin, temperatures warm or cold, gravity feels strange seasons, shift quick exotic skies, glow nights, sparkle bright moons, circle fast rings, shimmer wide, gas giants roar, rocky lands rise, life might flourish, water flows gently, winds sweep plains, strange creatures roam. Forests stretch, far mountains pierce clouds, valleys hide secrets, deserts stretch, endless glaciers drift, slow canyons carve deep, volcanic flames burn craters, mark old scars, rivers twist, slowly oceans teem. Quietly life adapts fast, evolution unknown environments test organisms thrive. Strange adaptations, eyes see differently, wings flap silently, camouflage perfect hunters, stalk prey, flee quickly. Microbes survive harsh extremes, are tolerated energy, flows freely, food webs, complex planets surprise humans, alien landscapes, vast colors unseen before, wonders await, their scientists dream big. Telescopes search far, satellites scan skies, data pours in, models predict growth possibilities, endless habitability. Varies, star types differ, planet sizes change, atmospheres mix elements, combine oceans, boil lightly, ice forms deep, suns warm slowly, moons affect tides, rotation speeds differ, day length changes, nights differ widely, climate is unique, life may adapt slowly, evolution moves, changes, create new forms, ecosystems balance, species interact delicately, habitats overlap, competition drives change, symbiosis thrives, energy cycles endlessly, photosynthesis adapts, life persists everywhere, curiosity drives. Humans, technology guides hope, exploration excites all discoveries, amaze planets. Observations expand knowledge, imagination grows rich, questions never end, stars shine distant, worlds beyond our reach. Planets may harbor life, unlike our own oceans, swirl unseen, atmospheres thick or thin, temperatures warm or cold, gravity feels strange, seasons shift quick, exotic skies glow, nights sparkle bright, moons circle fast rings, shimmer wide, gas giants roar, rocky lands rise, life might flourish, water flows gently, winds sweep plains, strange creatures roam, forests stretch far, mountains pierce clouds, valleys hide secrets, deserts stretch, endless glaciers drift slow, canyons carve deep, volcanic flames burn craters, mark old scars, rivers twist slowly, oceans teem quietly, life adapts fast, evolution unknown environments test organisms thrive, strange adaptations, eyes see differently, wings flap silently, camouflage perfect hunters stalk prey, flee quickly, microbes survive harsh extremes, are tolerated, energy flows freely, food webs complex planets surprise humans, alien landscapes vast colors unseen before, wonders await, their scientists dream big. Telescopes search far, satellites scan skies, data pours in, models predict growth possibilities, endless habitability varies, star types differ, planet sizes change, atmospheres mix elements, combine oceans, boil lightly, ice forms deep, suns warm slowly, Moons affect tides, rotation speeds differ, day length changes, nights differ widely, climate is unique, life may adapt slowly, evolution moves, changes, create new forms, ecosystems, balance species, interact delicately, habitats, overlap, competition drives change. Symbiosis thrives, energy cycles endlessly, photosynthesis adapts, life persists everywhere. Curiosity drives humans, technology guides hope, exploration excites all discoveries, amaze planets. Observations expand knowledge, imagination grows rich, questions never end. Introduction. Beyond our blue planet, when we think of Earth, we often imagine continents, forests, mountains, and deserts. Yet what defines our planet most is water, for it is more truly a blue planet than a green one. And most of that blue is not the shallow seas we know, but the abyssal depths we rarely see. More than 70% of Earth is ocean, and of that, the vast majority lies in darkness, far below the reach of sunlight, where pressure mounts like an invisible hand and temperatures hover just above freezing, creating conditions that seem unlivable to us, but that billions of organisms call home. For centuries, the deep ocean was dismissed as barren, an empty void where life could not survive. And yet, in the last 100 years, as technology has allowed us to descend into these hidden worlds, we have discovered ecosystems of astonishing richness and strangeness, worms without mouths, living on chemical energy, fish with transparent heads and lanterns of living light, crabs that farm bacteria on their claws, and corals that grow for thousands of years, older than entire civilizations. The deep is a realm of contradictions, a place of crushing pressure, yet fragile bodies, of perpetual darkness, yet dazzling bioluminescence, of scarcity of food, yet ingenious strategies for survival. And its landscapes are no less dramatic canyons, deeper than the Grand Canyon, mountain chains that span whole oceans, hydrothermal vents, hotter than boiling water, surrounded by life, and plains of mud, more expansive than any desert. But the abyss is not isolated. It is the beating heart of the ocean, a system that shapes global climate, recycles nutrients, and connects surface life with the seafloor through the rain of marine snow, the migrations of lanternfish and squid, the fall of whale carcasses that seed temporary oases of abundance, and the movements of sharks and whales that link worlds together. To descend into this hidden realm is to encounter both the familiar and the alien, to see that survival is written in patience, in partnerships with microbes, in light conjured from chemistry, and in bodies sculpted not to resist pressure, but to yield to it. The deep is humbling because, for all our satellites and maps, more than 80% of the ocean remains unexplored. Entire mountain ranges, coral forests, and species beyond imagination await discovery in silence, reminding us that we are strangers on our own planet. And yet it is not emptiness we find here, but mystery, not lifelessness, but a living archive of adaptation and endurance. This book is an exploration of those themes, not as a simple catalog of creatures, but as a narrative of resilience, of symbiosis and feeding strategies, of hunting dances and sudden strikes, of longevity measured in centuries, of reproduction carried out in darkness, of migrations that stitch together the water column, of microbes that sustain giants, and of defenses and connections that make survival possible in a world where mistakes are fatal. To look into the abyss is to confront the resilience of life and the boundless curiosity of humanity. To recognize that the unknown still vastly outweighs the known, and to feel wonder at the fact that in the greatest darkness of our planet, life not only survives but flourishes, inviting us to look deeper, think wider, and see our blue planet anew. The concept of habitability. What makes a world livable? When scientists speak of habitability, they are asking a deceptively simple question. What does it take for life to exist, endure, and evolve? At first glance, the answers seem obvious: liquid, water, a source of energy, the right chemical ingredients. But the more we study Earth, especially its hidden realms, such as the deep sea, the more complex the picture becomes. For habitability is not a fixed formula, but a spectrum shaped by context and adaptation. The abyss, for instance, is a world where sunlight never shines, where pressures crush submarines, where temperatures teeter near freezing or scalding at hydrothermal vents. And yet here, life thrives in forms once thought impossible, rewriting our expectations of what livable means. If microbes can draw energy from rocks, if worms can live on nothing but symbiotic bacteria, if fish can see in absolute darkness using bioluminescent lures, then the boundaries of habitability stretch far beyond the conditions that support humans. Habitability, then, is not simply about comfort, but about possibility. A planet or environment may be hostile to us, and yet a paradise to another form of life. This realization has transformed how we look beyond Earth. For moons like Europa and Enceladus, with their hidden oceans beneath ice, or planets like Mars, with hints of ancient rivers, are no longer dismissed as barren wastelands, but considered potential harbors of biology. What the deep teaches us is that habitability is not just about warmth or light, but about stability, chemistry, and energy sources. Whether from a star, a vent, or a reaction deep in rock, even within our own planet, from acidic hot springs to frigid trenches, life persists in environments once declared uninhabitable, suggesting that the concept of a livable world must be stretched wide enough to include places unimaginably different from our own. Ultimately, habitability is less about a single recipe and more about adaptability, about the ability of life to bend, stretch, and redefine the rules of survival. The abyss shows us that what we once thought of as rare or impossible may, in fact, be common, and that in searching the cosmos for life, we must keep our definitions open, for the universe may host creatures that, like the denizens of Earth's deep sea, thrive in conditions we once thought could never sustain them. The Goldilocks zone, not too hot, not too cold. Astronomers search for a narrow band of possibility, a region around each star where temperatures are just right for liquid water to exist on, a planet's surface neither boiling away into steam nor locked eternally in ice, a region they call the Goldilocks zone. The name evokes a story of balance worlds that are not too hot and not too cold, but somewhere in between, a place where seas might form, where rivers could flow, and where chemistry has the chance to take the leap into biology. On Earth, this balance has proven essential, for water is not merely a solvent, but the medium in which life first sparked and in which it continues to thrive, carrying nutrients, shaping climates, and sustaining ecosystems, from shallow reefs to the deepest trenches. Yet, the more we look at habitability, the more we realize that the Goldilocks zone is both a useful guide and an oversimplification, for Earth itself contains environments that defy the rule life thrives in scalding vents, in frozen glaciers, in acidic pools, reminding us that the boundaries of what is just right are wider than we once believed. Still, the zone serves as a cosmic shorthand, a way to sift through billions of planets, highlighting those with the best chances of surface oceans and stable climates. For while life might emerge in extremes, liquid water remains the most universal ingredient we know. Planets too close to their stars risk runaway greenhouse effects, as Venus demonstrates, while those too far risk becoming frozen deserts like Mars. And yet, even these so-called failures may hide secrets, for Mars once flowed with rivers and lakes, and Europa, far beyond the solar system's traditional habitable zone, harbors an ocean beneath ice, warmed not by sunlight, but by tidal forces. The Goldilocks zone, then, is less a strict line than a starting point, a reminder that while stars define boundaries, planets and their geologies, atmospheres, and orbits can bend the rules. It is a concept born of balance, but one that must be paired with humility, for the universe continually shows us that life finds ways in places we would least expect. To speak of the Goldilocks zone is to acknowledge the need for temperate waters and stable climates, but also to remember that our search for life cannot be confined to a single equation of distance and temperature. Instead, it must be guided by imagination as much as by measurement. For if the deep sea has taught us anything, it is that life thrives in conditions far beyond the narrow comfort we once assumed, and that the cosmos may hold countless worlds, each with its own version of just right. Liquid water, the key ingredient for life. When we speak of life as we know it, we almost always speak of water, for water is not just a substance, but the stage on which biology unfolds, a solvent that dissolves nutrients, transports energy, and enables the chemical reactions that knit molecules into cells and cells into living beings. On Earth, every form of life depends on it, from the forests that drink rainfall to the microbes that cling to grains of ice. And even in the deep sea, far from sunlight, water remains the constant presence, carrying heat from hydrothermal vents, distributing nutrients in slow currents, and suspending fragile creatures in its embrace. What makes liquid water so extraordinary is not only its abundance on Earth, but its unique chemistry. It is a polar molecule, able to dissolve a vast array of substances, to store heat without boiling away, to freeze from the top down in protective layers of ice that shield life below, and to flow across landscapes, carving valleys, rivers, and coasts. For this reason, astronomers scan the skies for planets where water might remain liquid, balanced between freezing and boiling, for where there is liquid water, there is at least the potential for life. Mars once bore rivers and lakes before its atmosphere thinned, leaving behind scars of a wetter past, while moons like Europa and Enceladus may harbor entire oceans beneath their icy shells, warmed not by sunlight, but by the flexing of tides, suggesting that water worlds may be more common in the cosmos than rocky deserts or volcanic giants. Yet water is not only about habitability in the abstract, it is about continuity, for on Earth it links all ecosystems, flowing from clouds to rivers to seas, evaporating and condensing in endless cycles, shaping climate, weather, and even geology. In the abyss, where marine snow drifts down as food, water carries the stories of the surface into the deep. And in frozen glaciers, pockets of liquid preserve microbes in hidden sanctuaries. To call water the key ingredient for life is to recognize that without it, our planet would be barren rock, our biology an impossibility, and our history unwritten. But it is also to acknowledge that life stretches the meaning of water beyond the familiar. Some microbes endure in brines so salty they approach saturation, others in acidic pools where water is scarcely recognizable as the clear liquid we drink, hinting that water's role may not always look like oceans and rivers, but still serve as the crucible of possibility. In our search beyond Earth, then, water is our beacon, a marker of where to look, a signal that chemistry might have a chance to awaken into biology. For while we may not yet know all the forms life can take, we know this much with certainty, that wherever liquid water flows, the possibility of life flows with it. Atmospheres that protect and nurture. If liquid water is the key ingredient for life, then an atmosphere is the vessel that protects it, a delicate skin of gases that shields a planet from the raw hostility of space, moderates temperature, and delivers the chemistry necessary for living systems to take root. On Earth, our atmosphere is more than just air we breathe. It is a layered guardian, filtering lethal ultraviolet radiation through ozone, scattering sunlight into the blue skies that warm our days, and trapping just enough heat through the greenhouse effect to keep oceans from freezing solid. Without it, Earth would swing between scorching heat in daylight and killing cold in darkness, an uninhabitable rock like the moon. The atmosphere not only protects but nurtures. It cycles water through evaporation and rain, spreads oxygen from forests and plankton, distributes carbon and nitrogen that fertilize soils and seas, and carries seeds, spores, and migrating animals across continents. Yet atmospheres are fragile, easily tipped into inhospitable states as seen in Venus, where runaway greenhouse gases turned the planet into a furnace hot enough to melt lead, or in Mars, where the loss of its magnetic shield allowed solar winds to strip away the air, leaving a thin, frigid veil incapable of sustaining surface water. In these failures, we glimpse the narrow balance that makes Earth so precious. For our own atmosphere has shifted dramatically in deep time. Oxygen was once absent, methane once abundant. Ice ages once gripped the globe, yet through each transformation, life adapted and sometimes even altered the air itself, as cyanobacteria did when they filled the skies with oxygen billions of years ago. This interplay between life and atmosphere is profound, for not only does the atmosphere nurture life, but life in turn reshapes the atmosphere, a feedback loop that may be the hallmark of a truly habitable world. Beyond Earth, when astronomers search for life, they look not only for water, but for atmospheres, for signatures of gases like oxygen, methane, or carbon dioxide that might hint at both stability and biology. A planet's air is both cloak and communicator, revealing its climate, chemistry, and potential. And while some worlds may shroud themselves in thick, toxic blankets or thin vapors of gas, others may achieve that precarious balance where protection and nurture coexist. Our own existence is possible only because of this fragile skin of sky, and in studying it, we are reminded that habitability is not a given, but a dynamic dance between geology, chemistry, and life itself. A reminder that in the great silence of space, even the thinnest atmosphere can mean the difference between a dead world and one that breathes. Gravity and planet size, holding an ecosystem together. When we think of what makes a world habitable, we often picture sunlight, water, and air. Yet, beneath them all lies a more fundamental force: gravity, the quiet architect that holds everything in place, shaping atmospheres, oceans, and even the bodies of living things. A planet's size, and therefore its gravity, determines whether it can cling to an atmosphere thick enough to shield life from cosmic radiation, or whether gases drift away into space, leaving only barren rock. Earth's mass is just right, large enough to hold onto nitrogen, oxygen, and water vapor, yet not so massive that crushing pressure smothers its surface like on Jupiter's giant moons. Gravity ties water to the planet's surface, allowing rivers and seas to persist instead of evaporating into space. And it orchestrates cycles of erosion, rainfall, and ocean currents that nourish ecosystems from mountaintops to trenches to little gravity, as on Mars, and the air thins to a whisper, leaving water unstable, freezing, or evaporating in moments. Too much, and an atmosphere can become suffocating, with gases piling thick until they trap deadly heat, as Venus demonstrates. Yet gravity does more than hold gases and water. It shapes geology itself, driving plate tectonics on worlds like Earth, recycling carbon through subduction and volcanic release, maintaining a climate balance across millions of years, and creating the mountains and basins that structure habitats. Even the pull of gravity from moons and neighboring planets can influence ecosystems, as Earth's tides, stirred by the moon, shape coastal life and nutrient flows, offering a subtle reminder that habitability is not a matter of isolation, but of gravitational relationships. For organisms, gravity defines what bodies are possible. Fish rely on buoyancy to counter Earth's pull. Trees grow strong trunks to resist collapse, and in microgravity experiments in space, even the simplest bacteria and human cells behave differently, hinting at how deeply life is tuned to its planet's weight. In imagining life on other worlds, scientists must consider how gravity would sculpt its possibilities. Would towering creatures thrive on low-gravity planets? Or would crushing gravity force life to remain small and close to the ground? In this way, planet size becomes a silent gatekeeper of habitability, influencing whether a world can hold its shield of gases, recycle nutrients, sustain water, and give life enough room to take root. Earth is not perfect by chance alone, but because its size and pull align with chemistry, energy, and time, making it a rare world where ecosystems hold together, stitched by the invisible threads of gravity. Energy from the star, sunshine, or something else. At the heart of every planetary system lies a star, a roaring furnace of nuclear fire that bathes surrounding worlds in energy, shaping their climates, atmospheres, and ultimately their potential for life and for Earth. The sun has been both the giver of warmth and the driver of almost every living process we know. Sunshine powers photosynthesis, the ancient trick by which plants, algae, and microbes turn light into food, building the foundation of food webs that stretch from forests to reefs. And it stirs winds, currents, and weather patterns that distribute heat and water across the globe. Without our stars' steady output, Earth would be locked in perpetual ice or seared into desert. Yet this dependence on stellar energy also reveals its fragility. For stars are not constant. Some flare violently, bombarding planets with deadly radiation, while others burn too weakly, leaving only frozen wastes. The so-called Goldilocks zone is defined by stellar energy, a band of distance where liquid water can endure. Yet even within that band, the quality of starlight matters. Cooler red dwarfs emit dim, reddish glow and frequent bursts of ultraviolet flares, while larger, hotter stars blaze so fiercely that their habitable zones lie narrow and fleeting, offering little time for life to take hold. But the deep sea on Earth has already taught us that sunlight, while powerful, is not the only path to survival at hydrothermal vents. Creatures thrive on chemosynthesis, drawing energy not from the sky, but from the chemical reactions of minerals pouring from Earth's crust, proving that biology can feed on fire and stone instead of light. This expands our imagination of habitability, suggesting that on distant worlds shrouded in ice, or on rogue planets drifting without suns, life might still persist, feeding on geothermal heat, radioactive decay, or tidal forces that warm hidden oceans. Even here at home, ecosystems show resilience to shifts in sunlight. Cave-dwelling species live in perpetual darkness. Deep ocean microbes find energy in the breakdown of methane, and some desert plants store light in fleeting bursts, eking out existence under extremes. Thus, while a star's energy is the most obvious source of life's fire, it is not the only one, and the search for habitability must embrace a spectrum of possibilities. Worlds where starlight nourishes forests, where volcanic heat sustains oceanic abysses, or where unseen chemistry sparks slow but enduring ecosystems beneath alien skies. To ask whether life requires sunshine is to ask whether life must look like Earth's. But the lesson of the abyss reminds us to think wider, that while stars are beacons of warmth and power, life may find other flames to feed on, hidden in the deep dark of worlds we have yet to see. Magnetic fields, shielding life from stellar storms. If atmospheres are the blankets that keep a planet warm and breathable, then magnetic fields are the invisible shields that guard it, silent guardians forged in the churning cores of worlds, deflecting streams of charged particles hurled outward by their parent stars. On Earth, our magnetic field arises from the slow, ceaseless motion of molten iron deep below, a geodynamo that creates a cocoon around the planet, bending the solar wind into sweeping arcs that would otherwise strip away our air and boil our seas. Without it, Earth's atmosphere might have suffered the fate of Mars, eroded over eons until only a whisper remained, incapable of protecting liquid water or shielding fragile life from radiation. The drama of this protection is rarely seen, but it reveals itself in the auroras, those shimmering curtains of green and purple that dance near the poles, where some particles slip through and collide with our upper era, breathtaking reminder of the constant battle between star and shield. 4 worlds orbiting volatile stars, particularly red dwarfs that unleash frequent flares. Magnetic protection may mean the difference between habitability and sterility. For even in the Goldilocks zone, Constant bombardment of radiation can sterilize surfaces and split water into gases that escape forever. A magnetic field is not only a barrier but a stabilizer, preserving atmospheric pressure, maintaining climates, and giving time for biology to adapt and flourish. Its absence can be catastrophic. Venus, though similar in size to Earth, lacks a significant magnetic field, and its atmosphere has grown dense and suffocating under solar assault. While Mars's once thicker air has been lost to space, its water locked in ice and rock. To consider habitability, then, is to consider not just the star, the orbit, or the air, but the hidden engine within, for without a molten, convecting heart to generate magnetism, a planet may be doomed to erosion and exposure. Yet even here, imagination stretches further. 4 subsurface oceans on icy moons may not need magnetic protection, as thick shells of ice serve as shields, and life in deep oceans might never feel the rage of a star at all, thriving in chemical sanctuaries hidden far below. Still, 4 Earth-like surfaces bathed in open skies. A magnetic field is nothing less than a planetary armor, a shield that turns lethal storms into beautiful lights, holding the line so that seas, skies, and ecosystems can endure. Early discoveries, planets in other star systems for most of human history. The stars were thought of as distant, unchanging lights, eternal pinpricks on the dark canvas of the heavens. Their twinkling beauty inspiring myths but never hinting at the worlds that might circle them. The idea of other planets orbiting other suns was whispered in philosophy and speculation, imagined by thinkers from ancient Greece to early modern astronomers. But it was not until the late 20th century that humanity finally began to peel back the veil and confirm that those distant lights truly host other worlds. The breakthrough came in 1992, when 2 small planets were discovered orbiting a pulsar, a dense, rapidly spinning remnant of a dead star, a strange and hostile place. For planets to be yet undeniable proof that planetary systems beyond our own existed. Just a few years later, in 1995, the discovery of 51 Pegasi b shook astronomy. For here was a gas giant orbiting a sun-like star only 50 light-years away, but so close to its star that its year lasted only 4 days. This hot Jupiter challenged everything scientists thought they knew, proving that planets could be far stranger than the neat, orderly arrangement of our solar system. From that point onward, discoveries multiplied, at first by painstaking measurements of stars wobbling under the gravitational tug of unseen companions, and later by the exquisite precision of space telescopes like Kepler, which watched for the faint dimming of stars as planets passed in front of them. Each new detection revealed not only that planets were common, but that they came in bewildering varieties: super-Earths, larger than our world but smaller than Neptune, mini-Neptunes cloaked in thick atmospheres, scorched rocky planets hugging close to their stars, and mysterious worlds drifting alone without suns. What had once been speculation transformed into a revolution, the realization that planets are not rare jewels, but cosmic commonplace, scattered across the galaxy in almost every system we can observe. The early days of exoplanet discovery were marked by awe and surprise. Each new find a reminder that our solar system is not a template, but just one example among countless possibilities. and that the conditions for life may be written into the very fabric of the universe. In those first glimpses of alien worlds, we caught sight not only of planets, but of ourselves, dreamers staring across light years, humbled by the enormity of creation and newly aware that our search for life was no longer confined to Earth, but had expanded into the infinite reaches of the stars. Kepler 4.5 to be Earth's cousin 1,000 light-years away in 2015. The announcement of Kepler 452b sent ripples of excitement through both the scientific community and the public imagination. For here, at last, was a planet that seemed to echo Earth, in both scale and circumstance, orbiting within the habitable zone of a star not unlike our Sun, located more than 1,000 light-years away in the constellation Cygnus. Kepler 452b was quickly dubbed Earth's cousin, a world about 60% larger than our own, circling its star every 385 days, almost a mirror of our familiar year. Its star, slightly older and brighter than the Sun, suggested a planet bathed in steady warmth, where liquid water might still flow across landscapes we can only dream of. The discovery felt momentous because it was the first rocky planet found in the habitable zone of a Sun-like star, a milestone that seemed to move the idea of another Earth from the realm of speculation into tantalizing possibility. Yet, as with all exoplanets glimpsed from afar, Kepler 4.5b remains a mystery wrapped in distance. We cannot yet know if it holds oceans or air, continents or clouds, or whether its greater mass makes it a super-Earth with crushing gravity or a miniature Neptune swaddled in thick gases. Still, the symbolism mattered as much as the science. For Kepler 450 to be crystallized, the notion that Earth is not alone in the universe, that worlds resembling ours may be scattered across the galaxy in great number, waiting for more advanced telescopes to bring their features into focus. Its star's advanced age also sparked reflection. If life did take hold there, it may have had billions of years more than Earth to evolve, raising haunting and exhilarating questions about civilizations that could exist under its alien sun. Kepler 4.5 to be reminded us that the search for habitable worlds is not merely a technical pursuit of numbers and data, but a profound extension of human curiosity, a quest to see ourselves reflected in the cosmos, and to imagine the landscapes where other stories of life might be unfolding, even now, beyond the reach of our light, but not beyond the reach of our wonder. Proxima Centauri b, a neighbor in the Alpha Centauri system. Among the most thrilling discoveries of recent years is Proxima Centauri b, a planet orbiting the red dwarf Proxima Centauri, the closest star to our Sun and part of the Alpha Centauri system, only a little more than 4 light-years away, a mere step, cosmically speaking. Detected in 2016 through the subtle wobble it induces in its parent star, Proxima b instantly captivated scientists and dreamers alike. For here was a potentially Earth-sized world sitting within the habitable zone of its star, tantalizingly near in astronomical terms, close enough that we can already imagine future probes reaching it within centuries, or perhaps even decades, if technology accelerates. Its minimum mass is comparable to Earth's, suggesting it could be rocky rather than gaseous, and it orbits its faint star every 11 days. A short year, but one that still allows just enough warmth for liquid water, depending on its atmosphere. Yet, its star, unlike our Sun, is volatile. A red dwarf prone to flares and bursts of radiation that may strip away air and sterilize surfaces, leaving open the question of whether Proxima b is a cradle for life or a barren, blasted rock. Some models suggest it could be tidally locked, with one face locked in perpetual daylight and the other in eternal night, creating extreme environments where life might cling only in the twilight zone between. Others hold hope that a thick atmosphere, magnetic protection, or oceans could buffer such extremes, making Proxima be a world of dramatic skies and strange climates rather than a dead husk. Its nearness makes it especially compelling, for unlike more distant exoplanets, Proxima b lies within the realm of conceivable exploration. The Breakthrough Starshot initiative has even imagined launching swarms of tiny, light-driven craft to race across interstellar space and capture its first close-up glimpses. Whether or not it proves habitable, Proxima b symbolizes the turning of possibility into proximity, the knowledge that the search for another Earth need not stretch only into unfathomable distances, but begins with our nearest star, reminding us that the galaxy may hold not just distant cousins like Kepler 452b, but neighbors next door, waiting silently under alien suns. TRAPPIST-1e, F, and G worlds in a tight, habitable dance. Few discoveries have fired the imagination quite like the TRAPPIST-1 system, a dim, ultra-cool dwarf star just 40 light-years away, orbited by 7 Earth-sized planets, packed so tightly together that from one world, the others would loom large in the sky like bright moons. Among them, TRAPPIST-1, E, F, and G stand out as the most tantalizing, all lying within or near the star's habitable zone, where conditions might allow liquid water to persist. These 3 siblings form a kind of cosmic harmony, locked in orbital resonance that keeps them stable. Their years measured not in hundreds of days, but in short, elegant rhythms, 6, 9, and 12 days respectively. Yet, even in their rapid orbits, they remain cool enough to stir hope of seas, skies, and life. Each planet is close in size to Earth, rocky rather than gaseous, and early models suggest TRAPPIST-1e could be one of the most Earth-like exoplanets yet found, with densities hinting at a solid surface and perhaps even an atmosphere capable of supporting temperate climates. TRAPPIST-1, F, and G, slightly larger and farther out, may be cooler but could host thick atmospheres or icy shells above hidden oceans, echoing the possibilities of Europa or Enceladus in our own solar system. The sheer intimacy of the system, with planets packed so tightly that sunlight takes only minutes to cross from one orbit to the next, means that these worlds are not isolated, but part of a delicate cosmic choreography influencing one another, with gravitational tugs and perhaps even exchanging material through impacts, raising the astonishing possibility of life spreading between them. For astronomers, the TRAPPIST-1 system is not just remarkable for its worlds, but for its accessibility. Their transits across their tiny star make them perfect targets for telescopes like James Webb, which can probe their atmospheres for hints of water vapor, oxygen, or other biosignatures. To imagine TRAPPIST-1e, F, and G is to picture not a lone oasis, but a chain of potential havens, a family of worlds locked in tight embrace, orbiting a faint red star that glows barely brighter than Jupiter in our sky, yet hosting perhaps one of the best chances to find life beyond Earth. In their dance, we glimpse not just the diversity of planets, but the possibility of entire systems, where habitability is not the exception but the rule, and where, under the light of a tiny sun, alien ecosystems may rise and fall in unison, echoing across worlds that watch one another in their eternal celestial waltz. LHS 1140b, a rocky planet with water potential amid the catalog of nearby exoplanets. LHS 1140b shines as one of the most promising candidates for habitability. A rocky super-Earth orbiting a small, dim red dwarf star only about 40 light-years away in the constellation Cetus, discovered in 2017 by the transit method, where conditions could allow liquid water to exist on its surface. Larger and more massive than Earth, about 1.5 times its size, and more than 6 times its mass. LHS 1140b likely boasts a dense, rocky composition with the gravity to hold on to a substantial atmosphere, a vital ingredient for sustaining surface water. Unlike some red dwarf systems plagued by violent stellar flares, LHS 1140 is relatively quiet, bathing its planet in steady, gentle light. Because its star is small and faint, the planet orbits very close, completing a year in just 25 days. Yet the reduced stellar output means its surface temperatures could be moderate if its atmosphere distributes heat efficiently. The possibility that LHS 1140b harbors oceans has stirred excitement. For water is the universal solvent of life as we know it, and the combination of rocky terrain, stable conditions, and potential atmospheres make this world one of the prime targets for next-generation telescopes. Instruments like the James Webb Space Telescope are already poised to peer into its skies, searching for chemical signatures of greenhouse gases, water vapor, or even biosignatures that could hint at active biology. What makes LHS 1140b so captivating is that it represents not an abstract possibility, but a tangible nearby world we might one day study in exquisite detail. A real place, orbiting a real star whose light still reaches our telescopes. It stands as a reminder that even around the smallest, faintest stars, planets can emerge that feel familiar. Worlds where seas might glisten under alien skies, and where the story of life could be quietly unfolding, just beyond our reach. Kepler 2 to be the first confirmed super-Earth in 2011. The discovery of Kepler-22b marked a milestone in humanity's search for other worlds, for it was the first time astronomers confirmed a planet larger than Earth residing within the habitable zone of its star. A quiet, sun-like star located about 600 light-years away in the constellation Cygnus. The planet itself, about 2.4 times Earth's radius, quickly earned the title of super-Earth, a category of worlds unknown in our own solar system, straddling the line between rocky giants and small gas planets. What captured attention was not only its size but its orbit, a gentle 290-day year around a star slightly smaller and cooler than our Sun, a balance that places Kepler-2 to be within the so-called Goldilocks zone, where temperatures might allow liquid water to pool if conditions are right. Yet, even as it stirred imaginations, Kepler-2 to be also highlighted the challenges of interpreting distant data. For while we know its size and orbit, its true nature remains elusive. Is it a rocky world with oceans spread across its surface? A water-rich planet cloaked in deep seas beneath a thick atmosphere? Or a mini Neptune with a gaseous envelope too heavy for life as we know it? Its discovery showed both the promise and the limits of the Kepler mission, which opened a floodgate of detections but often left unanswered questions about composition and habitability. Still, Kepler 2b holds a special place in the exoplanet story, not because it is the most Earth-like candidate, but because it was the first to confirm that such planets larger than Earth, orbiting within the habitable zone of distant stars, are real and not just statistical predictions. It shifted the conversation from if to how many, reminding us that the cosmos is rich with possibilities and that every new detection brings us closer to understanding where life might flourish. For many, Kepler 2b became a symbol of hope, a landmark on the journey of discovery, showing that the universe not only hosts alien worlds, but also worlds that may, in their broad outlines, resemble our own atmosphere clues, signs of oxygen and water, if the surface of a distant world remains hidden from our eyes. Its atmosphere becomes the canvas upon which the story of habitability is painted, and astronomers have learned to read those faint chemical signatures carried across light years like whispers from alien skies. When a planet passes in front of its star, starlight filters through the thin veil of gases surrounding it, and with careful instruments we can detect the fingerprints of molecules such as oxygen, water vapor, carbon dioxide, that may reveal whether a world is barren or brimming with potential. Water vapor is the most immediate prize, for it suggests clouds, rains, and oceans that could nurture life, while oxygen, especially when found alongside methane, hints at processes beyond simple chemistry, processes that on Earth are sustained by biology. Yet the search is riddled with complexity, for oxygen can also emerge from non-living processes, such as the splitting of water molecules under intense starlight, and methane can bubble up from geological activity, meaning that no single gas is proof of life. Instead, scientists look for patterns, for the delicate balance of gases that resist easy explanation without biology, a harmony of chemistry that points toward metabolism, respiration, or photosynthesis. The detection of such atmospheric signatures is one of the great frontiers of exoplanet science, made possible by telescopes like James Webb, which can peer deeper into alien skies than ever before. Each spectrum gathered, each dip of starlight measured, is like decoding a secret language that might one day tell us with scientific confidence that we are not alone. Atmospheres are fragile, shaped by geology, climate, and stellar winds. Yet in their transparency lies our best hope of glimpsing life across the gulf of space, not in the form of creatures or cities, but as faint traces of oxygen and water written into the very air of another world. Surface conditions, land, oceans, and weather patterns. When we imagine distant worlds, it is often their surfaces that capture our imagination, for it is there upon continents, in seas, beneath shifting skies, that the drama of habitability unfolds. Yet piecing together what those surfaces might be like from so far away is an extraordinary challenge. Some exoplanets may be dominated entirely by water, vast ocean worlds with no land at all, their surfaces wrapped in endless blue, broken only by storms and tides, while others may be dry, rocky expanses with deserts stretching under alien suns, landscapes sculpted by winds that carry strange particles instead of familiar dust. Weather patterns, too, may differ wildly from those of Earth, driven not only by a planet's tilt and rotation, but by the whims of its star. Tidally locked worlds could host bizarre climates, with one hemisphere scorched in unending daylight, and the other frozen in eternal night, the only temperate regions lying along a narrow twilight band circling the globe. Gas-rich atmospheres might produce thick, permanent cloud decks, veiling surfaces in perpetual gloom while trapping heat, creating hothouse conditions, or alternatively, shielding planets from harsh stellar radiation. On some super-Earths with stronger gravity, weather may be denser and more turbulent, storms towering higher and winds blowing faster than anything we know. Even on worlds that resemble our own, the distribution of land and water could reshape the story of life continents, forming isolated evolutionary laboratories or global oceans, fostering life without ever allowing it to reach dry land. Though we cannot yet see these surfaces directly, models and data hint at their diversity, and the study of land, oceans, and weather patterns on exoplanets reminds us that habitability is not a single state, but a spectrum of possibilities, a range of worlds that may be harsh, strange, or surprisingly familiar. In these imagined surfaces, we glimpse the potential for alien climates, alien ecosystems, and alien skies, all bound by the same universal physics that shape our Earth, yet expressed in countless variations across the galaxy. Star type and radiation. How the host star shapes life. The nature of a planet's star is as vital to its habitability as the planet itself. For the type, size, and behavior of a star dictate not only how much energy a world receives, but also the quality of that energy and the stability of the environment that life must endure. Around stars like our Sun, conditions can be relatively stable, with a steady output of light and warmth that fosters long-term climates where complex ecosystems might flourish, but smaller. Cooler red dwarfs, the most common stars in the galaxy, present a double-edged promise. Their habitable zones are close in, allowing planets like Proxima b or the TRAPPIST-1 worlds to orbit snugly within reach of liquid water. Yet that same intimacy exposes them to powerful stellar flares, surges of radiation, and charged particles that can strip away atmospheres and sterilize surfaces unless a planet possesses magnetic fields or thick protective layers. By contrast, larger, hotter stars burn brighter but live shorter lives, often only a few 100 million years, perhaps too brief a span for life to emerge and evolve into complexity, leaving their habitable zones more like fleeting opportunities than stable havens. Radiation itself is both a threat and a possibility, capable of breaking apart molecules and driving harmful mutations, but also, paradoxically, sparking the chemistry that might give rise to life in the first place, as it may have done on early Earth. The spectrum of starlight matters, too. Red dwarfs bathe their planets in infrared light, which might shape alien photosynthesis into something entirely different from Earth's green. while blue-white stars flood their systems with high-energy photons that demand strong adaptations or protective niches for survival. Ultimately, every host star writes the rules of its planet's environments, sculpting atmospheres, climates, and evolutionary paths. To study the type and radiation of a star is to understand the stage upon which the drama of habitability is played, reminding us that worlds do not exist in isolation, but in constant, intimate dialogue with the fires that warm them. Tidal locking, day and night on other worlds, among the many strange fates that befall planets circling close to their stars. Tidal locking is one of the most dramatic, a gravitational grip that forces one hemisphere to face eternal daylight while the other is plunged into unending night, a condition that challenges our earthbound notions of climate, habitability, and even the rhythm of life itself. On such a world, the dayside may blaze under constant starlight, its surface scorched and atmosphere superheated, while the nightside freezes into a perpetual wasteland of ice and shadow. Yet between these extremes lies a twilight ring, a narrow band of eternal dusk where temperatures might be moderate enough for liquid water to persist, perhaps forming strange seas that shimmer under the dim glow of a star fixed forever at the horizon. Atmospheric circulation could blur these boundaries, with winds sweeping heat from day to night and currents redistributing energy across the globe, creating climates that are less hostile than the stark division suggests, while thick atmospheres or oceans could further moderate extremes, giving such planets a chance at stability. For life, tidal locking poses challenges, but not impossibilities. Organisms might adapt to constant light or darkness, evolving unique strategies for photosynthesis, navigation, or energy storage, while ecosystems could thrive in the twilight zone where conditions are neither too hot nor too cold. Some models even suggest that tidal locking might enhance habitability in certain cases, keeping planets warmer than they would otherwise be and allowing them to sustain liquid water around dim stars like red dwarfs. To imagine a tidally locked planet is to envision skies where the constellations never move, where one horizon burns in permanent dawn while the other lies beneath eternal stars, and to recognize that what seems alien and inhospitable to us may, for other forms of life, be simply the natural order. Tidal locking reminds us that habitability is not a single template, but a spectrum of adaptations shaped by the intimate gravitational embrace between a planet and its star. Comparative habitability. Could life thrive better than on Earth? When we dream of habitable worlds beyond our solar system, it is tempting to imagine only those that resemble Earth, with familiar continents, oceans, and skies. Yet the concept of comparative habitability asks a bolder question. Could there be planets where life not only survives, but actually thrives more abundantly than it does here? Earth, after all, is not perfect. It faces cycles of ice ages, mass extinctions, shifting continents, and long-term fluctuations in climate. And while these stresses have fueled evolution, they have also caused repeated setbacks for the flourishing of ecosystems. But what if somewhere in the galaxy there exists a planet slightly larger than Earth, with stronger gravity to hold a thicker atmosphere that stabilizes climate and protects against radiation? A world with vast, shallow oceans, ideal for biodiversity or with gentle weather systems that nurture life instead of battering it with storms. Some worlds may orbit stars that are quieter and longer lived than our sun, offering billions of years more stability in which life could emerge and evolve without interruption. Or they may boast nutrient-rich geology and continuous tectonic activity that recycles elements efficiently, fueling ecosystems in ways our own planet only intermittently manages. Perhaps there are super-Earths where life spreads across colossal continents and unbroken seas, or planets with twin suns providing longer growing seasons and more consistent energy for photosynthesis, creating lush environments that Earth can only hint at. The idea that life might find even better footholds elsewhere does not diminish our own world, but instead expands our imagination of what habitable truly means, not a single blueprint, but a spectrum of possibilities where some conditions surpass the delicate balances we depend on. Comparative habitability challenges us to think beyond Earth's limits, to accept that our home may be only one expression of life's potential, and that in the vast theater of the cosmos there may be worlds where life blossoms more easily, more widely, and perhaps more beautifully than we can yet conceive. Possibilities of alien flora and fauna for other worlds harbor life. Then the question naturally arises, not only of its existence, but of its form. And in contemplating alien flora and fauna, we step into a realm where science and imagination intertwine, guided by biology, chemistry, and the constraints of physics. On planets orbiting red dwarf stars, for instance, alien plants might evolve dark pigments to harvest the weak, infrared-rich light, carpeting their worlds in shades of black, deep crimson, or even metallic hues that reflect harmful radiation. While on brighter worlds with twin suns, vegetation could shimmer with iridescent layers to regulate the influx of energy, creating forests that glisten like jewels. Fauna, too, would reflect their environments and high-gravity super-Earths. Creatures might grow low and stocky, hugging the ground to conserve energy. While on low-gravity planets with thick atmospheres, animals might drift, glide, or even fly with ease, their wings spanning wider than anything possible on Earth. In perpetual darkness, life could turn bioluminescent, entire ecosystems glowing with soft blues and greens, while in worlds of eternal day, eyes might shrink or vanish, altogether replaced by senses tuned to heat, vibration, or magnetic fields. Alien bodies might be built not from proteins and DNA, but from alternative chemistries, silicon-based instead of carbon, or using solvents like methane or ammonia instead of water, producing organisms whose metabolisms and structures are utterly unlike our own yet still obey the universal rules of survival. Predator-prey dynamics could still exist, but they might look unfamiliar giant filter feeders drifting through alien seas, crystalline grazers feeding on mineral-based flora, or creatures with body plans unimaginable to earthbound evolution. Though our vision of alien life is often shaped by Earth's diversity, the possibilities stretch far beyond, reminding us that biology is an artist that adapts endlessly to environment, resource, and constraint. In envisioning alien flora and fauna, we do not merely dream of monsters or exotic gardens. We expand our understanding of what life might mean in a universe that has had billions of years to explore possibilities far stranger and perhaps far more beautiful than we can conceive. Oceans under ice, life hidden in darkness beneath the frozen shells of distant moons and exoplanets may lie vast oceans locked away from starlight, realms where life could persist in utter darkness, sustained not by sunshine but by the hidden energies of geology and chemistry. Worlds like Europa, Enceladus, and perhaps countless icy exoplanets orbiting far from their stars remind us that habitability is not always tied to warmth from above, but can be preserved in the depths below, where tidal flexing from gravitational forces keeps water liquid. In these alien seas, hydrothermal vents might spew minerals and heat into the cold abyss, creating chemical gradients that serve as the engines of metabolism. Just as similar vents on Earth's ocean floors gave rise to thriving ecosystems without any reliance on the sun, life here would be adapted to extremes microbes clustering near energy sources, complex organisms perhaps evolving in niches where chemistry and heat align, all moving through waters illuminated only by bioluminescence, soft glows that mimic starlight in places where stars will never shine. An icy crust above could act as both shield and trap, protecting oceans from deadly radiation and preserving them for billions of years, while also cutting them off from the sky, locking life into an isolated existence where evolution follows. Unique and unpredictable paths. If alien oceans exist in such hidden sanctuaries, the creatures within may be utterly unlike our expectations, fluid, flexible, and deeply tied to the chemical pulse of their environment, surviving on energies unfamiliar to us yet universal in principle. These worlds remind us that habitability is not always obvious to the eye. A frozen desert from the outside may conceal within it a vibrant oceanic cradle, proving that where water persists, even beneath ice and in darkness, the spark of life may endure. Super-Earths and mini-Neptunes, extreme environments for life among the most common types of exoplanets discovered so far are those that fall between the size of Earth and Neptune. Worlds larger than our own but smaller than the gas giants, known as super-Earths and mini-Neptunes, and their abundance raises profound questions about the possibilities of life in environments that are at once familiar and alien. Super-Earths, with masses up to 10 times greater than Earth, may be rocky planets with vast mountain ranges, stronger gravity, and thicker atmospheres that could stabilize climates, protect against stellar radiation, and sustain oceans that lasts for billions of years. Yet that same gravity could also pose challenges to life, making movement more costly and evolution favoring compact, resilient forms. Many Neptunes, by contrast, may be cloaked in thick, gaseous envelopes. Their surface sith, they exist at all buried under crushing atmospheres of hydrogen and helium, creating environments that seem hostile to life as we know it. Yet within their dense atmospheres could exist temperate cloud layers, niches suspended in the sky where pressure and temperature might resemble Earth's. A floating ecosystem akin to the hypothesized potential for life in the clouds of Venus. Some super-Earths might hold vast oceans, hundreds of kilometers deep, water worlds without continents, where geology and biology play by different rules. while others could be dry and barren, their atmospheres stripped away by stellar winds. Mini-Neptunes might transition into super-Earths if their gaseous envelopes erode over time, exposing rocky cores that could become stable and habitable surfaces. The sheer diversity of these planets challenges the boundaries of our imagination, suggesting that life could emerge under pressures, gravities, and chemical balances that Earth never experiences. To study super-Earths and mini-Neptunes is to explore the most common laboratories of nature in the galaxy, where the extreme becomes ordinary, and to realize that among their countless variations, some may harbor environments not only capable of sustaining life, but of sustaining it in forms we have not yet dreamed of. Alien skies, colors, sunsets, and atmospheres. To look up at the sky of another world would be to witness a canvas painted by physics, chemistry, and light, each atmosphere shaping its own alien beauty, from the soft scattering of starlight to the radiant glow of strange sunsets. On Earth, our blue skies and fiery orange evenings are the result of sunlight filtered through nitrogen and oxygen. But on a planet with a different atmospheric mix, the view could be radically transformed. A carbon dioxide-rich sky might appear, pale orange or pink throughout the day, while methane-heavy air could give everything a hazy green or purple tint, and thicker atmospheres might scatter light so completely that the sky glows in deep, perpetual twilight. Worlds orbiting red dwarfs could bask under dim crimson skies, where sunsets bleed into violet horizons, while planets around blue-white stars might experience dazzling brilliance, with daytime light so sharp and stark that shadows appear jet black. On water worlds cloaked in vapor, the heavens might be layered with endless cloud bands, while desert planets could shimmer with dust-filled skies that scatter light into hues of copper and gold. Even the act of sunset itself might differ on tidally locked planets. The star never moves, creating a sky of eternal dawn or dusk, while on planets with dense atmospheres, light could bend and linger, stretching the moment of sunset into hours of surreal color. Alien skies would not only be spectacles of beauty, but also vital clues to habitability, their colors revealing the composition of air, the presence of water vapor, or even the gases of life itself, such as oxygen and methane, in delicate balance. To imagine these skies is to imagine the emotional worlds they inspire, beings who grow under crimson canopies or permanent twilight may perceive the universe differently than we do. Yet the shared act of looking upward unites us in wonder. Alien skies remind us that every planet wears its own atmosphere like a cloak, and that somewhere beyond our blue, other horizons are glowing with colors we have yet to see. Gravity and movement, how life adapts to different strengths. The quiet sculptor of worlds dictates not only the shape of planets and the flow of oceans, but also the very possibilities of life's form and movement. And to imagine creatures evolving under different gravitational strengths is to explore biology under new and radical rules. On high-gravity super-Earths, where every step would feel like carrying a heavy burden, life might be compact, muscular, and low to the ground, with stocky forms built to resist crushing weight, wings rendered useless and replaced by powerful limbs designed for stability rather than speed, and forests that grow squat and dense, their trees spreading wide rather than tall, to support their own mass. By contrast, on low-gravity worlds or moons with thick atmospheres, evolution might favor creatures that leap and glide with ease, their bodies elongated and lightweight, with vast wings or sail-like appendages that let them drift on gentle winds, while plants might rise in slender, fragile towers, stretching higher than Earth's redwoods without fear of collapse. In extreme cases, life may not even cling to a surface at all. In the sky oceans of gas giants, organisms could float in buoyant layers, adapted to balance in shifting atmospheric currents. Their movements less like walking or swimming and more like drifting in three-dimensional seas of air. Gravity shapes not only bodies, but also behaviors. Predators on high-gravity worlds might ambush rather than chase, conserving energy, while on low-gravity planets, prey might survive by launching themselves into the air, turning escape into a graceful bound. Even internal biology would differ. Hearts would beat harder under greater pressure. Bones would need to be denser or replaced with flexible frameworks, while in low gravity, circulation might be easier but orientation more difficult, requiring senses attuned to balance in an environment where up and down are less defined. Gravity, in its invisible pull, writes the laws of motion for every ecosystem, reminding us that life is never separate from its environment but is shaped, step by step and leap by leap, by the weight of the worlds it calls home. Chemical richness, ingredients for complex life forms. Life, in all its complexity, is ultimately a dance of chemistry, a weaving of elements into structures that can grow, replicate, and adapt. And when we speak of the possibility of alien organisms, we must first consider the chemical richness of their worlds, the raw ingredients that make life possible. On Earth, carbon is the backbone of biology, forming vast chains and intricate molecules, while hydrogen, oxygen, nitrogen, phosphorus, and sulfur join it to create the essential scaffolding of proteins, nucleic acids, and cell membranes. Yet, these elements are not unique to our world. They are forged in stars and scattered throughout the galaxy, waiting to be assembled into life's architecture wherever conditions allow. Planets with volcanic activity, tectonic recycling, or cometary bombardments may accumulate rich chemical inventories, while subsurface oceans and hydrothermal vents could brew complex organic molecules in abundance, just as Earth's early seas may have done. The diversity of elements on a world's surface and atmosphere dictates not only the potential for biology, but also its possible pathways. On some planets, life may still be carbon-based, but with entirely different solvents, like ammonia or methane, altering biochemistry in ways that yield unfamiliar metabolisms. While in others, silicona, versatile, though less flexible, element might form the foundation of alien cell structures. Trace metals such as iron, magnesium, and copper, so critical to Earth's enzymes and oxygen transport, could vary from world to world, giving rise to creatures with blood that runs green, black, or even violet, each adapted to their unique planetary chemistry. The richer and more varied the chemical palette, the greater the potential for complexity. For complexity thrives on diversity, and worlds with wide arrays of elements and active cycles to circulate them may host life more intricate, resilient, and inventive than anything we know. To imagine chemical richness is to imagine possibility itself, the raw materials of biology scattered across the cosmos, waiting for the right balance of chance and stability to awaken into forms that think, move, and perhaps even wonder. Just as we do, time scales, lifespans, and evolution on other planets' time, though measured universally by the ticking of physics, is lived differently by life. And on other planets, the scales of lifespans and evolution could diverge dramatically from those we know on Earth, shaped by environment, chemistry, and cosmic rhythm, on a stable, temperate super-Earth with few extinctions. Organisms might evolve slowly, developing intricate and long-lived ecosystems where creatures measure their lives in centuries or even millennia, their evolutionary pathways stretching across vast epochs of relative calm. By contrast, on volatile worlds marked by frequent asteroid impacts, volcanic upheavals, or radiation storms, life may burn bright and fast, organisms living brief lives and evolving rapidly in an endless cycle of destruction and renewal, driven by survival in a precarious environment. The length of a planet's day, year, and seasonal cycles could influence biological clocks on worlds with long days and nights. Creatures might adapt with lifespans attuned to extreme cycles of activity and dormancy, while on tidally locked planets where time is divided into eternal day and night, life might evolve rhythms entirely unfamiliar to us. Gravity and metabolism play their roles. Two high-gravity worlds might favor slow-moving, energy-efficient organisms that grow steadily and endure, while low-gravity planets could foster lighter bodies that burn energy quickly, leading to shorter lives. Evolution itself may unfold at speeds alien to our expectations. Abundant mutation-inducing radiation could accelerate the branching of new forms, while protective magnetic fields and calm climates might slow change, allowing species to persist for eons with little alteration. Some worlds may harbor microbial life that has remained simple for billions of years, content in stable niches, while others could give rise to complex, intelligent beings in geological instance compared to Earth's gradual path. Time for alien life is both a constraint and a canvas, a force that molds not only individuals but entire biospheres, reminding us that the tempo of existence is not universal on other planets. Lifespans may outlast civilizations or vanish before a single breath would pass on Earth, and evolution itself may compose symphonies, either drawn out and delicate or urgent and explosive, each shaped by the clock of its world. Planetary ecosystems, predator, prey, and food chains wherever life takes hold. It weaves itself into networks of energy and survival, and on alien worlds, planetary ecosystems would form around predator, prey, and food chains just as they do on Earth, though the shapes and strategies of those interactions might be astonishingly different. At the foundation would be the producers, organisms that capture energy, whether from starlight, chemical reactions, or geothermal heat and convert it into usable fuel, forming the base upon which entire ecosystems are built. Above them would rise consumers of every scale, from tiny grazers nibbling at microbial mats to immense predators sculpting the flow of evolution with their hunger. On high-gravity planets, prey may evolve low, armored bodies to resist attack, while predators become ambushers that strike with sudden bursts rather than long chases, conserving energy in heavy environments. On low-gravity worlds, predators might glide or leap after swift airborne prey, transforming hunts into three-dimensional pursuits across sky and land. In oceans under ice, entire food webs could flourish without sunlight, dependent instead on chemosynthetic organisms clustering around hydrothermal vents, their energy cascading upward into strange grazing creatures and predators that stalk in darkness. Even the roles themselves might blur predators, becoming prey in cycles of mutual dependence or symbiotic partnerships, replacing the rigid hierarchies we expect. Apex predators could be enormous, highly specialized beings ruling vast territories, or they could be small, agile creatures wielding toxins, camouflage, or bioluminescence as weapons in ecosystems where size does not guarantee dominance. Food chains might not even follow familiar patterns. In methane-rich atmospheres, alien herbivores could feed on chemical producers, while predators digest hydrocarbons rather than proteins, creating biologies whose metabolisms are unlike anything on Earth. Yet, whatever the details, the universal truth remains that energy must flow, cycling through living systems, shaping behaviors, adaptations, and balances of power. To imagine planetary ecosystems is to envision worlds alive with motion and tension, where predator and prey evolve in step with one another, weaving a web that is fragile and enduring all at once, a living network that ties each species to the survival of the whole. The role of moons, stabilizing orbits, and climate moons, often regarded as silent companions, can, in truth, be architects of planetary stability, shaping the conditions under which life might arise and endure, for their gravitational pull influences far more than tides can stabilize a planet's tilt, regulate its climate, and even guide the rhythms of ecosystems. Earth's own moon provides a vivid example by anchoring the tilt of our planet's axis. It prevents wild swings that could otherwise send climates lurching from extremes of ice to furnace-like heat, ensuring instead the relative stability that has allowed life to evolve over billions of years. On worlds without such stabilizing companions, axial wobbles might be violent, flipping poles toward the star or plunging them into endless cold, creating climates too chaotic for complex life to gain a foothold. Moons also drive the tides, stirring oceans, mixing nutrients, and perhaps even playing a role in the emergence of early life. Along shifting shorelines where wet and dry cycles fostered complex chemistry, in other systems, multiple moons could create intricate tidal rhythms, with ecosystems evolving in harmony with cycles more elaborate than Earth's daily ebb and flow. While giant moons orbiting gas planets might even host atmospheres of their own, becoming life-bearing worlds in their own right. Yet moons can also be disruptive. Too large a companion might lock a planet's rotation or drag it into unstable orbits, while small distant moons may offer little influence at all. Still, when balanced, a moon can serve as a cosmic guardian, smoothing a planet's path through time, lending it the steadiness needed for climates to stabilize, oceans to circulate, and life to persist. To consider the role of moons is to realize that habitability may not depend only on a planet and its star, but also on the quiet, persistent influence of companions orbiting in the night sky. Unseen shapers of destiny whose presence or absence could decide whether a world becomes barren or blooms with life. Human imagination. How these worlds inspire dreams from the moment humanity first looked up at the night sky and traced patterns in the stars. We have filled the darkness with stories, and the discovery of distant worlds has only deepened this impulse, igniting our imagination with visions of alien landscapes, creatures, and civilizations. These planets and moons, though separated from us by unimaginable distances, serve as mirrors for our hopes and fears. A lush, Earth-like world might embody our longing for renewal, a second home where life could flourish again, while a barren, storm-swept giant might symbolize endurance in the face of chaos. Science fuels this imagination by revealing just enough truth to invite wonder. An exoplanet in the habitable zone. An ocean beneath the ice. A strange atmosphere with hints of chemistry that might suggest life, and from these fragments we spin entire worlds in our minds, populated by beings that walk, swim, or soar in ways both familiar and alien. Writers, artists, and dreamers extend science into myth, crafting stories of thriving alien civilizations or lonely, silent planets that still hold beauty in their desolation. Yet, imagination is not mere fantasy. It is also a compass, guiding science itself, inspiring missions, telescopes, and theories that reach ever further into the cosmos. Every imagined alien sky or ocean stirs questions about ourselves, how unique we are, how fragile our own world may be, and how deeply we are connected to the wider universe. These worlds, whether they host life or remain barren, remind us that existence is vast, that possibility is boundless, and that in seeking to know the unknown, we also discover our own boundless creativity. In the end, alien planets are not just places to be studied, but canvases for human wonder. Reminders that imagination itself is one of our greatest tools in bridging the gap between what we know and what we dream. Exoplanet exploration missions, telescopes and probes. The search for other worlds is not just a feat of imagination, but a triumph of technology. And exoplanet exploration missions, whether telescopes scanning the skies from Earth's orbit or probes pushing deeper into our cosmic neighborhood, form the vanguard of this quest to uncover the unknown. With the launch of the Kepler Space Telescope, humanity first glimpsed the staggering truth that planets are common, discovering thousands of worlds orbiting distant stars and showing us that our solar system is only one among countless others. Kepler was followed by TESS, the transiting exoplanet survey satellite, which broadened our vision, finding nearby planets small enough to study in detail, while ground-based observatories sharpened the search with precision measurements of starlight. Today, the James Webb Space Telescope takes this exploration to a new level, not only detecting planets, but peering into their atmospheres, hunting for signatures of water vapor, carbon dioxide, methane, or even the faint whispers of life's chemistry. Yet telescopes are only the beginning. Future missions, such as LOVEWAR, HABEX, or the extremely large telescope, promise to directly image Earth-like planets, capturing pale blue dots beyond our own, while probes and robotic explorers may one day venture outward, First, 2 icy moons in our solar system, like Europa and Enceladus, and eventually to interstellar space, carrying with them humanity's instruments and questions into the dark. Each mission, from the first detection of a planet's dim transit to the dream of interstellar sails propelled by starlight, represents a step in a journey that is as much about ourselves as it is about the cosmos. The desire to know if we are alone, the drive to push boundaries, and the recognition that the universe is not a backdrop but a vast frontier waiting to be explored. These telescopes and probes are our eyes and hands across the void, extending human presence far beyond our fragile sphere. Each discovery, a reminder that exploration is not a luxury but a destiny, woven into the fabric of what it means to be human. The Drake equation, estimating life in the universe. When astronomer Frank Drake first wrote down his now famous equation in 1961, he was not trying to solve the mystery of alien life, but to frame it, to give structure to a question as vast as the stars themselves. How many civilizations might exist in our galaxy capable of communication? The Drake equation is not a single answer but a chain of probabilities, multiplying together factors such as the rate at which stars form, the fraction of those stars with planets, the number of habitable worlds in each system, the likelihood that life emerges, the chance that intelligence evolves, and the duration such civilizations might broadcast their presence into space. Each variable holds both hope and uncertainty. Some, like the frequency of planets, are now illuminated by telescopes such as Kepler and TESS, which reveal that worlds are abundant, while others, like the probability of life's emergence, remain cloaked in mystery. The beauty of the equation lies not in precision, but in perspective. It shows us that the existence of intelligent life depends not on one miracle, but on a cascade of chances, a cosmic lottery where each step could open the way or close the door. To some, the equation suggests we may be surrounded by countless civilizations, hidden only by distance and silence. To others, it underscores the possibility that we are rare, perhaps even alone, our voices echoing unanswered in the dark. Yet, the Drake equation has endured not because it settles the debate, but because it sharpens it, turning vague wonder into measurable questions that guide science and imagination alike. Every new discovery of exoplanets in habitable zones, of organic molecules on comets, of complex chemistry in interstellar clouds fills in another blank, nudging the probabilities and reshaping our estimates of what is possible. In the end, the equation is less a solution than a mirror, reflecting our desire to understand our place in the cosmos and reminding us that to seek an answer is itself part of being alive, part of the long human tradition of looking upward and wondering who else might be looking back. Extremophiles on Earth. Clues to alien survival if we wish to imagine how life might persist on alien worlds. We need only look at Earth's own extremophiles, organisms that thrive where survival seems impossible, turning hostile environments into unlikely sanctuaries. These tiny pioneers live in boiling hydrothermal vents where water scalds beyond 100 degrees Celsius, in the frozen deserts of Antarctica where liquid water is scarce, in acidic pools that would dissolve most life, and in crushing depths of the ocean where sunlight never penetrates and pressures would crush human-built machines. Some endure radiation that would obliterate DNA, while others enter dormant states that allow them to survive for millennia, waiting for conditions to turn favorable again. Each of these adaptations demonstrates that life is not fragile but astonishingly versatile, capable of rewriting the rules we once thought defined habitability. For alien oceans sealed beneath ice, extremophiles on Earth that live around chemical vents show how energy can fuel entire ecosystems without sunlight. For toxic atmospheres rich in methane or sulfur, microbes that metabolize such compounds here remind us that alien metabolisms may be built on chemistry utterly unlike our own. Even in space itself, tardigrades' tiny water bears have survived the vacuum and radiation, suggesting that the seeds of life could endure journeys between worlds. The lesson of extremophiles is profound. The boundaries of habitability are not fixed, but elastic, shaped by life's ability to adapt, endure, and transform. In studying them, we glimpse not only the resilience of our own planet's biosphere, but also the possibility that alien survival may be commonplace in environments we once dismissed as barren. Each extremophile on Earth is a living clue, a reminder that if life can thrive in boiling acid, crushing darkness, or frozen wastelands here, then the universe may be far richer in living worlds than we ever dared to imagine. Planetary climate, storms, winds, and seasons. Climate is the heartbeat of a planet, a dynamic interplay of atmosphere, rotation, orbit, and stellar energy that weaves together storms, winds, and seasons into patterns that can shape the very possibility of life. On Earth, this balance creates familiar cycles of rainfall, monsoons, hurricanes, and the slow turning of seasons. But elsewhere, the forces at play can sculpt climates far more extreme and alien. On Jupiter, colossal storms rage for centuries, including the Great Red Spot, a cyclone larger than Earth itself, while Neptune's winds roar at supersonic speeds, sculpting clouds into shifting ribbons of ice and methane. Planets close to their stars may be locked in perpetual daylight and night, one hemisphere scorched and the other frozen, where winds could circle the planet endlessly in attempts to balance the heat, creating climates unlike anything we know. Tilt and orbit further shape planetary moods. A world with a high axial tilt might endure violent seasonal swings where poles alternate between blistering heat and endless winter, while planets in eccentric orbits could lurch from searing summers. 2 glacial ice ages in a single year. Dense atmospheres, like Venus's crushing cloak of carbon dioxide, can trap heat in runaway greenhouses, turning the surface into a furnace, while thin atmospheres, like Mars's, allow wild swings between scorching days and freezing nights. Storms, winds, and seasons are not only weather, but also sculptors of landscapes, creators of deserts, oceans, and fertile plains, and potential catalysts for life's rhythms driving migrations, cycles of reproduction, and the distribution of nutrients. To imagine alien climates is to imagine worlds alive with motion, skies painted with endless tempests, continents reshaped by seasonal floods, or quiet planets where calm stability persists for eons. In every case, climate is destiny, a reminder that beneath the stars, the personality of a world is written not only in its rocks and seas, but also in the restless dance of its atmosphere. Future discoveries. What we might find in the next decade. Next decade promises to be a golden age for exoplanet science. A time when technology and curiosity converge to push the boundaries of what we can know, transforming questions of possibility into discoveries that reshape our place in the cosmos. With the James Webb Space Telescope already peering into distant atmospheres, we may soon detect the first clear evidence of water vapor, methane, or even oxygen on alien worlds, chemical hints that could mark the presence of life. Upcoming missions, such as ESA's Plato, NASA's Roman Space Telescope, and ground-based giants like the extremely large telescope, will sharpen our gaze, allowing us not only to find Earth-sized planets around sun-like stars, but also to study their climates, seasons, and compositions in unprecedented detail. We may witness the first direct images of blue oceans or clouds on exoplanets, or discover strange, superhabitable worlds, planets larger and older than Earth, offering even richer conditions for life. Closer to home, probes exploring Europa and Enceladus could confirm the existence of liquid oceans beneath the ice, and perhaps even detect organic molecules or microbial life swimming in the dark. Beyond biology, we may uncover exotic planetary types that defy imagination: diamond planets, tidally locked water worlds, or rogue planets wandering the galaxy without stars, each reshaping our definition of habitability. Even the search for technosignatures, radio signals, laser flashes, or atmospheric traces of industrial activity may yield its first tantalizing results, expanding the Drake equation from theory to evidence. What makes this decade so thrilling is not only the discoveries we anticipate, but also those we cannot yet imagine. The surprises that will force us to rewrite our understanding of life, planets, and the universe itself. As new data streams in, each revelation will bring us closer to answering humanity's oldest question: are we alone? Or are the skies filled with neighbors waiting to be found? The search for biosignatures, detecting life remotely if we are ever to confirm the existence of life beyond Earth. It may not be through a direct encounter, but through the delicate art of detecting biosignatures, those faint, telltale fingerprints left in the atmospheres, surfaces, or spectral patterns of distant worlds. Biosignatures are the silent echoes of biology, the chemical imbalance of oxygen alongside methane, the spectral glow of chlorophyll-like pigments, or even unusual atmospheric patterns that cannot be explained by geology alone. Telescopes, such as James Webb, are already scanning exoplanet atmospheres for these subtle markers, while future observatories like Lovewar and Habix may sharpen their vision enough to detect light filtered through alien skies, revealing whether clouds, oceans, or plant-like pigments reflect the starlight in ways we recognize. Even a single, robust biosignature would be transformative, for it would mean that life is not a singular accident of Earth, but a cosmic phenomenon threaded into the fabric of the universe. Yet the search is delicate, for false positives lurk everywhere. Volcanoes can produce methane, photochemistry can mimic oxygen, and mineral surfaces can imitate the spectral signals of life. This is why scientists emphasize the need for multiple lines of evidence, a chorus of signals pointing toward biology rather than a lone, ambiguous whisper. Beyond Earth-like life, researchers are also considering exotic biosignatures, such as organisms that might metabolize sulfur, silicon, or ammonia, creating atmospheric compositions unfamiliar to us but consistent with alien biochemistries. The challenge is immense. We are trying to read the breadth of another world from light years away, but the reward is equally profound. For in those faint signatures lies the possibility of answering the question that has haunted humanity since the beginning. Are we alone, or is life a common companion in the universe, waiting patiently to be discovered through the lens of a telescope? Terraforming dreams. Could humans improve a planet? The idea of terraforming, reshaping an alien world to make it more Earth-like, has long been one of humanity's boldest dreams. A vision that hovers between science and science fiction, blending engineering with imagination. The concept is simple in theory, but staggering in practice. Take a barren planet such as Mars, with its thin atmosphere and frozen deserts, and gradually warm it, thicken its air, and seed it with the ingredients for life until it could support forests, oceans, and eventually human settlements. Proposals range from releasing greenhouse gases to trap heat, to placing giant orbital mirrors that reflect sunlight, to importing volatile-rich comets that could deliver water and atmosphere in great icy impacts. Others suggest building vast networks of microbes or engineered organisms that could slowly transform alien soil and skies, echoing how cyanobacteria on early Earth once filled the atmosphere with oxygen. Yet the obstacles are immense. Gravity, radiation, magnetic fields, and geological stability all play roles that cannot be easily altered, and the timescales may span centuries or millennia. Moreover, the ethical questions are profound. Should we alter another world before we know if native life exists? And does humanity have the right to reshape entire ecosystems for its own survival? Still, the dream persists because terraforming is not only about engineering planets, but about reimagining human destiny. To terraform is to declare that we are not bound to Earth alone, that with knowledge and patience we might carry the spark of life to barren places and watch them bloom into new homes for future generations. Whether it remains forever a dream or becomes one of history's greatest achievements, the idea of terraforming reminds us that the boundary between the possible and the impossible is always shifting, and that humanity's greatest frontier may not only be the stars we reach, but the worlds we transform along the way. Ethical reflections. Observing without interfering as humanity edges closer to detecting life beyond Earth, whether microbial traces in alien oceans or complex ecosystems under foreign skies. An urgent question arises. Should we merely observe, or do we have the right to interfere? The history of exploration on our own planet warns us of the dangers of intrusions, species driven to extinction, environments disrupted, and cultures overwhelmed by careless contact. Applied on a cosmic scale, the stakes are even higher, for any life we encounter may represent billions of years of evolution, entirely unique to its world, fragile and irreplaceable. The principle of planetary protection argues that our first duty is to safeguard these ecosystems from contamination, both from Earth microbes hitching rides on spacecraft and from human curiosity that may disrupt delicate balances. At the same time, Some argue that withholding exploration out of caution denies us opportunities to learn and to expand our understanding of life's diversity. The balance between curiosity and caution becomes an ethical frontier as vast as space itself. Should we seed barren planets with life, or would that erase the possibility of discovering what nature might have achieved on its own? Should we mine alien worlds for resources, or protect them as natural reserves of the cosmos? In grappling with these questions, we are forced to recognize that exploration is not only a technical challenge, but a moral one, requiring humility, foresight, and respect for life in all its forms. Observing without interfering may be the most difficult path of all, but it may also be the truest way to honor the profound mystery of existence, allowing alien worlds to tell their stories without being overridden by our own cosmic perspective. Earth in the context of the universe. To see Earth in the context of the universe is to confront both our smallness and our significance, a paradox that deepens the more we learn about the cosmos. From the vantage point of space, our planet is a fragile blue dot, suspended in darkness, a sliver of light in the vast sea of galaxies. Yet within its oceans and soils exists every story of life we know. Astronomers tell us there are more stars in the universe than grains of sand on Earth's beaches, and around many of those stars orbit planets, some rocky, some gaseous, some icy, and perhaps a few alive with their own forms of biology. Against this immensity, our world is not central, not privileged, yet it is precious beyond measure, for it is the only place, so far, where life has been confirmed to thrive. Looking outward grants us perspective inward. The boundaries of nations dissolve when seen from orbit, and the conflicts that dominate human history shrink against the backdrop of infinite stars. Earth becomes not a divided map, but a shared home, a single oasis whose atmosphere shields us, whose magnetic field protects us, and whose ecosystems nurture us. To frame Earth cosmically is also to realize how fragile its balance is. Climate, biodiversity, and atmosphere, all finely tuned over eons, vulnerable to disruption, yet essential for life. This perspective calls for humility, reminding us that our planet is one among billions, but also for responsibility, for the uniqueness of our world places a duty on us to protect it while we search for others. In the grand sweep of the universe, Earth may be small, but it is not insignificant. It is our cradle, our teacher, and perhaps the first stepping stone on a journey that will carry life, curiosity, and wonder out into the wider cosmos. Closing. Reflection, wonder, curiosity, and the endless sky as we reach the end of this exploration. What lingers most is not just the science of distant worlds, nor the mechanics of stars, atmospheres, and orbits, but the profound sense of wonder that such knowledge awakens within us. To gaze upward is to confront questions older than civilization itself, questions of origin, of belonging, of destiny, and, though the universe offers no simple answers, it continually invites us to keep asking. Curiosity is the light that guides us through darkness. The same impulse that once carried humans across oceans and deserts, now carrying us across light years in thought and in vision. Every discovery, from the first exoplanet to the faintest whisper of a possible biosignature, is not an ending but a beginning. expanding the horizon of what we can imagine and deepening our awareness of how much remains unknown. The endless sky is both a mirror and a mystery. It reflects our drive to explore, to learn, and to dream, while concealing countless worlds that may one day reveal themselves to our eyes and instruments. To live under this vast cosmos is to accept that we are part of something immeasurably greater, yet capable of reaching toward it with minds and machines that extend far beyond the limits of our bodies. Wonder keeps us humble. Curiosity keeps us restless. And the sky, in its endlessness, reminds us that the story of discovery will never truly close. Each chapter we write about the universe is only a prelude to the next. And as long as humans look upward, the journey will continue, carried forward by hope, imagination, and the eternal allure of the stars.